go. Let's see if it's going to pick it up. Might have shrunk.
We turn off one side of the lights.
Yeah. Close these blinds too. Okay. I get all my tools in hand. Acids and bases. Much of our discussion of acids and bases is going to pick up with equilibrium. Acids and bases are, it's not the only characteristic of acids and bases, but it's a major part, and that's calculations involving equilibrium. So first we need to define what an acid let's start with acids. Arrhenius proposed that acids were those compounds that possessed in them a dissociable hydrogen ion, at least one, sometimes more. And that when it was dissolved in water, that hydrogen ion or proton became separated from the molecule. And it would look like, this is our generic acid, right? There's your proton, and there's what's left over. So that could be almost anything. And then in aqueous solution, what happens is that proton separates. It gives you that. So obviously, this is set up for an equilibrium expression. I'm not going to write one for that now because we're going to advance a little more in history and concept before we get to that point. Arrhenius also said that a base was anything that possessed a hydroxyl polyatomic ion. And in aqueous solution, that also separated. Something like that. Now, even today, many acids and bases follow this pattern, right? But eventually there were instances where you would get an acidic or a basic solution and you couldn't trace it directly to a proton or a hydroxyl on the original molecule. Right, so Bronsted and Lowry independently came up with this idea. They proposed that acids were actually proton donors. Right? So in that respect, their acids were much like Arrhenius, but that bases were proton acceptors. So that opened the field a little bit. For instance, why would dissolving this in water produce a basic solution? There are no hydroxyls there, right? Dissolve ammonia in water and you get a basic solution. That's the reality, and the theory has to jive with reality. So what happens is it reacts with water because there's plenty of it there. And so when ammonia reacts with water, one of these protons from ammonia is transferred to that. And what's left over here is the hydroxyl. So we've produced a hydroxyl, it's just not by the Arrhenius model. Okay, so that's Bronsted-Lowry, and that has stood the test of time for aqueous solutions of acids and bases. When we get to the place where we're trying to conduct acid-base type reactions in non-aqueous solutions, then, of course, this one falls apart because there's no water there to react. So we need another definition, and that's where we come to the Lewis acid and base concept. But we're not going to hammer on that one right now. We'll get to Lewis acids and bases later, maybe not even till organic. I can't remember if we get to it in general chemistry or not. Okay, so according to Bronsted and Lowry, what happens in aqueous solution for this acid is that it transfers that proton to water. So that makes it a proton donor. And it's the acid. And in this case, that makes water the base because it's the proton acceptor. And what we have is an acid and a base reacting to produce, let me do this. Okay, so if this is the donor and this is the acceptor, then what we get on this side is the conjugate base of the acid. And for the base, we get the conjugate acid. Now, if you look at this in terms of equilibrium, remember an equation that's written in this way, the reaction can go both directions. And in fact, it does. So if you have an acid producing a conjugate base, that means that this now is a proton acceptor. Right? So it can accept a proton either from this water, this ion, which has a special name. That's the hydronium ion. It can accept a proton back from that and produce these products. Or it can go and accept a proton from water. Theoretically. It could accept a proton from water, become hydrochloric acid again, and that would produce a hydroxyl. The reason I say theoretically is because this being a strong acid makes this a weak base. And we'll talk about that in a minute. A weak base doesn't accept protons very well. Right? So that reaction I proposed, where it would accept a proton from water, doesn't happen. That's just theoretical. Okay, so what actually happens at the molecular level? If we take this model where ammonia interacts with a water molecule, then there's the proton that is originally part of the water molecule and is being pulled toward the ammonia molecule. Now, this process is reversible, of course. And it depends on the strength of the attraction of that hydrogen ion. As it turns out, this reaction, where you have ammonia in aqueous solution reacting with water to produce the ammonium ion and the hydroxyl ion. The equilibrium for this reaction is way, way, way over here. Okay, it's well over 90% ammonia. That's the form. Okay, so you only get a little bit of this. It's enough to make the solution basic. I'll grant you that.
7.2.
I'm sorry?
So like 7.2.
No, it's a little higher than that. It's just that the equilibrium itself is way over here, favored to this. We'll talk about actually calculating pHs because they're dependent on two things: the equilibrium constant and the equilibrium position. Right? So we can make it more basic if we just increase this. Right? So that changes the equilibrium position to give us more of this and a more basic solution. But if you only have just a tiny amount of this that you add to the water, then yeah, you could conceivably produce a 7.2 pH solution. Okay, so that tug of war is actually in favor of water. That's what keeps it over here at this side. And also, there's lots of water, and the molarity of pure water is in the neighborhood of 45 molar. It's pretty high.
So ammonia is the base?
Is the proton acceptor. Yes, that makes it the base. And that makes this the acid. So that's leading us toward the concept of water can be either one. Depends on the situation. Water could be an acid, could be a base. And of course, while all this is going on, there's a whole lot more water out there than there is ammonia. So there's competition with this molecule with other water molecules for interactions with the water. Okay, we're going to talk about that in a minute. Oops. I think I'm going to need sound, so I better get it up.
The Bronsted-Lowry concept defines acids as proton donors and bases as proton acceptors. In the reaction of aqueous hydronium ions and ammonia molecules, the hydronium ion acts as the Bronsted-Lowry acid and the ammonia molecule as the Bronsted-Lowry base. The net effect is that of a proton transfer from hydronium to ammonia, forming water and the ammonium ion.
Now see, they took a different reaction there. What they're saying is that this water, actually, I should redraw that. And I'll just go ahead and give you this one. Pure water will do this. One water will be the acid, another water will be the base. And what it will do is produce that. It'll just transfer one proton from here to here. Actually, I flipped them. I should put the OH over here. Because this is the acid, this is the conjugate base. And this is the conjugate acid of that base. Okay, so these two are related and these two are related. So in that scenario, they're saying that when you put ammonia in water, the ammonia is actually going to take a proton from the hydronium ion. Okay? But the net effect is the same as the first reaction.
So it's kind of like an elementary step.
Yes. So that reconstitutes the water that was formed by this reaction. But notice that when we couple the two reactions, you're removing this one, but you're doing nothing with that one. So you still got the hydroxyl there. Either way you draw it, you end up with hydroxyls. OHs, yes. So the way I wrote it up there at first was kind of like saying this is a net reaction. And this is, like you were saying, elementary steps. Not exactly elementary as our kinetics discussion involved, but nonetheless, they're coupled reactions. Okay. So we've done that before and defined the conjugate acid, conjugate base.
Acid ionization in water is an equilibrium reaction. Acetic acid ionizes in water to a small degree, forming hydronium and acetate ions. Because of the small degree of ionization, and because water is nearly a pure liquid, we rearrange the equilibrium constant expression. If we now remove water from both the chemical and equilibrium equations, we get the acid ionization constant for water. The Ka for acetic acid is 1.7 times 10 to the minus 5. The animation sequence shows acetic acid reacting with water to form hydronium and acetate ions. At equilibrium, both the forward and reverse reactions proceed at the same rate, such that the net concentration of each ion remains constant.
Okay. Have you heard that before? Last chapter, right? So what they're saying is that even though the acetic acid, I'm going to draw acetic acid this way. And the reason I'm doing it that way is to show you that this is the hydrogen that dissociates, not these, that one only. And when it does that and reacts with water as a base, it produces this conjugate base and this conjugate acid. Okay? Then when we write the equilibrium expression, we put this one times that one divided by this one. And since we never include solids or pure liquids, solids or pure liquids are left out, then the expression only includes those two and this one. So the Ka, remember when I said the subscript for K has a lot to do with how of the meaning of the K, right? So the Kas are acid dissociation constants.
This is probably a bad question considering just a test on it at the time. What's KC stand for?
Yeah, I didn't know.
Concentration.
Concentration.
Yeah.
Moles per liter.
Yeah, it'll be molar.
So if there was a typo that said 7.5 liters per mole, I was correct. So it was supposed to be moles per liter.
Oh, was there a typo?
Just one. It said that K is equal to 7.5 liters / moles.
Oh, no, that could be. Yeah. But that just illustrates the point that we usually don't put units in there because they can be so weird. So this one is this expression for the equilibrium constant, Ka, for acetic acid in aqueous solution. It's just that. And they said the value was 1.7 times 10 to the minus 5th.
So the acetic acid is just considered aqueous, or?
Oh yeah, it's aqueous. Excuse me.
So I guess I get confused with that and how you said like the H2O is the pure liquid and then we don't include it because it's a pure liquid. And that's because.
Oh, I see what you mean. It's a solute, right? But the concentration is so high in these solutions that it doesn't change, right? It stays relatively constant during the entire process.
So it's just kind of.
So it's kind of it's buried in that term right there.
Just the carrier for the.
Right, for the acid. Mm-hmm. Right, it's a solute.
So if we see the little L, just don't count it like we did
Don't
with the
count it.
solid.
Right.
But if it's aqueous, those are the things we're concerned with, like we were with gases.
Yeah, that's true. So what does this mean? In terms of equilibrium, look how small that number is. That means these terms are very small compared to this one, which means that there's very little of this over here. Most of it's over here.
Small k means reactants are favored.
Exactly.
I learned that the last chapter.
Okay. If, however, instead of acetic acid, which is a weak acid, we encounter a strong acid like hydrochloric acid, the dissociation of hydrochloric acid is almost complete, almost total to the right. So it would be right up here again. Put it down here. And then you would have that plus this, right? And you would find that calculating an equilibrium constant for this reaction is almost meaningless because it's so huge. I think it has been done, but for all intents and purposes, none of that is left. It's all over here. That's the nature of strong acid. The ionization equilibrium lies far to the right. Now, so what does that mean? If this is a strong acid and the reaction is driven way over here to the products, what driving force is there for this to return? Practically nothing drives it for the reverse reaction to occur, which means if this is the acid, strong acid, that means this is the weak conjugate base.
Conjugate being defined as.
The consequence of an acid losing its proton. It produces a base because now, theoretically,
That CO wants to take the hydrogen.
it doesn't necessarily want to, but it is capable of.
It's weak, so it doesn't.
Right, it doesn't really want to, but according to the Bronsted-Lowry definition, it can be a proton acceptor. It's just not.
That H3O, I guess, being the conjugate acid means it wants kind of to give off an H.
Yes. It is a proton donor, right? We can say proton donor without implying strength. Or we can say proton acceptor without implying strength. But if we look at a weak acid, just the converse is true. The conjugate base for the weak acid is strong. Because it prefers to be over here, that means there is a very strong attraction of this anion for protons.
Does that mean that the reaction would be kind of pushing to the left more?
Yes, oh yes, way, way over here. Right.
Would it be the reverse of HCl in water?
Yeah, it wants to be over here.
Because the Cl is very okay with not having a proton into it.
Right.
What is that chemical that is,
Siggy?
what is the chemical called? What is that, the CH3COO? What is that?
Oh, that's acetic acid.
No, I didn't say the last H. What is it on the other side of the equation?
Oh, this?
Yeah, what's that?
Oh, that's the acetate ion.
Acetic ion.
Right.
It's a strong conjugate base.
In that list of polyatomic ions, it's written this way.
Okay, you said acetate ion?
Acetate. Yes. It's a polyatomic ion. So it can be combined with any cation. It can be sodium acetate, ammonium acetate. Those are possibilities. Okay. So the difference between a strong acid and a weak acid is which side of the reaction do they prefer? Right? Strong acid prefers product, weak acid prefers reactant. Okay. This is just a summation. This is a table that came straight out of your book. It just summarizes what we've said so far.
You just said a weak acid prefers
Reactant.
reactant.
Reactant, yes. Other strong acids?
So weak acids, could you generalize and say weak acids have a very small K value then? Is that a general truth?
Yes. Their Kas are very small.
Oh, that's right on the next chart.
Okay.
Good job, Rain.
Hydrochloric, nitric, actually HBr and HI are both strong acids also. They're part of this family. Now the odd thing, I'll point this out now, we'll talk about it later. This one is weak. It's in the same family as the halogens, and these are strong acids, HI, HBr, HCl. But HF is a weak acid. And the reason for that is that the negative ion, F minus, is very small and has a very high charge density as a consequence. In other words, it's got the same charge as these others, as the anion, but it's concentrated in a small area, so it has an even stronger pull on protons.
So it really wants to hold on.
It does, yes. That's one way to look at it. The other way to look at it is electronegativity. It's very, very high electronegativity. Gives it that increased charge density. Okay. Now I'm going to leave that one up there, except for what I accidentally erased. Conjugate acid. Okay, this demonstrates the autoionization of water. Pure water, and this time I do mean pure water, nothing else dissolved in it, will react with itself. So you have one water molecule acting like an acid and the other one like a base, and you get this reaction. And the expression, the equilibrium expression for this one is the hydronium times hydroxyl. That's it. Because these are both L's. Right? This one's given a special subscript, KW. And the value is 10 to the minus 7, or 1 times 10 to the minus 7.
Is that one very specific? So it's very.
Oh, excuse me. Ooh, that's bad. 14.
Oh.
Sorry.
Wait, okay, so it's 10 to the negative 13.
Yes, I'm sorry.
Okay.
Each one of these is 10 to the minus 7. So that makes this 10 to the minus 14. When it dissociates at about 25 degrees centigrade, you get 10 to the minus 7th molar hydronium and 10 to the minus 7th molar hydroxyl. And that makes sense because you've got water reacting with water, so if you get this, where did it come from? Well, it came from there. Where did this come from? Well, it came from there too. So they have to be equal. And in pure water, they do have to be equal. Okay, this characteristic autoionization of water is called amphoterism. Water is amphoteric. Sometimes it's called amphiprotic. That means it can go both ways. Yeah, right. That's just the same Greek prefix. Yep.
So at 25 degrees Celsius, water just does this.
Yep, sure does. And that's not bad.
What is that in Fahrenheit?
Huh?
What is that Fahrenheit? What is that?
25 degrees centigrade?
Yeah.
Well, 20 is 68 Fahrenheit. So 25 would be 9 plus this one would be 77. Okay. I do that when I drive by banks, you know, with those thermometers on their thing. They go Celsius, and then a few seconds later they go Fahrenheit. Well, I'm driving by, so if I see Celsius, I'm gone before the Fahrenheit comes up. So I know this relationship. I know 20 degrees is always 68. So if I go up 5 degrees, I got 77. If I go down 5 degrees, I got 59. That's because of the ratio of centigrade to Fahrenheit units is 9/5. So for every 5 of these, 9 of those. That's just a way to estimate. Okay. And this value is always the same, no matter what we do. So if we were to add some protons to that solution using a strong acid, it would influence this one, but the KW for water would still be that value, which means if we increase this one, that one has to go down. Right? So if we added enough, say our starting position is this right here, molar. So if we increase this one, say 10 to the minus 6th molar, by adding some protons, then this one would have to go down to 10 to the minus 8. Right? Because this is a constant. It has to be obeyed. That's the constant value. So if we change this one, got to change that one. Right? That's characteristic of all aqueous solutions. Okay. Now, this situation right here is what we call neutrality. That's a neutral solution, pure water. We can make neutral solutions by adding stuff to it, but we always have to obey this relationship no matter what we do to it. If we have this relationship, 10 to the minus 7, 10 to the minus 7 equals that, this is neutral. Right? The scenario I just showed you where this goes up to 10 to the minus 6, this one goes down to 10 to the minus 8, that's acidic. And you just keep going down. If you add more, this one goes down 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1. Down there, those are all acidic. If we increase this one by, say, adding hydroxyls, if we make this one 10 to the minus 6, that makes this one 10 to the minus 8, right? Now, we're defining a basic solution. And as this one continues to increase, remember, these are negative powers, so the smaller the negative number, the higher the concentration. Minus 6, minus 5, minus 4, get bigger and bigger and bigger. And hydroxyls, then you've got a basic solution. And as a consequence of this relationship, this has to get smaller as you go. Okay? So another way of saying that is, if we're starting at this is equal to that, then if this is bigger than that, if hydrogen ions are bigger than hydroxyls, and that's quirky, I guess, with acid-base nomenclature and reaction. We're equating this one with this one. Right? For all intents and purposes, they are the same. Okay? We just have to recognize that we say hydrogen ion concentration, but hydrogen ions never ever exist as free protons in solution. They're always associated with something. If nothing else, they associate with water, make hydroniums.
What would push it one way or the other?
Oh, additions or subtractions, right? If you add hydrogen ions in the form of a strong acid like hydrochloric acid, then that will make this bigger than that. Okay. If we add sodium hydroxide, you know, grandma's lye, then that'll make this one bigger than that. And now you've got a basic solution. Okay? This is a fundamental relationship. Everything in acid-base chemistry in aqueous solution hinges on that relationship right there. No matter what else you do, that has to be obeyed. Okay. So this is a generic Ka for an acid in water. Right, there's your hydronium, there's your conjugate base, right here we see on that side, divided by the acid. And of course, the one with the L doesn't count.
K, subscript little a.
Yeah,
For acid.
Yeah, I tried to change that before I threw it up on the screen, but I didn't have the tools to do it with. So that should have a little a right here. So if the equilibrium lies to the right, the value of Ka is going to be large. definitely greater than 1. If the equilibrium lies to the left, which means weak acid, then the Ka is going to be small and most definitely less than 1.
It's pretty intuitive.
I'm sorry?
It's pretty intuitive.
Yeah.
It just means that it's small and the bottom number is really big, so the reactants are really big concentration.
Yes.
There's the larger K, stronger acid.
Right. Right. Okay. All right. We're gonna run out of time if I linger on this problem. We might have to tackle some of these things with our review. And after you've had a chance to look at it and had your heads turned inside out a couple of times, then we're ready to talk.
Guaranteed.
Okay, so we will stop for this one. If you have a 1 molar solution of HCl, then, and I'm going to abbreviate this, rather than put the water in there, I'm going to say that dissociates to these two. Order them in the, they order them by strongest to weakest base. Okay, so that means that this is strong acid. So that means this is weak base. In fact, the weakest base. So this is going to be on this end. That's the weakest base.
Hydrochloric acid is the strongest acid.
No, I think hydroiodic is stronger than hydrochloric. The reason being, remember, as this charge density decreases, right, the ions get bigger, but it's still got the same charge. That charge density means that it can't hold on to the proton as well, and it wants to release it. Okay, so next is a weak acid. So if this is a weak acid, and we're producing, this is a strong base. In fact, a very strong base. So that means this one goes over here. So by process of elimination, water's in the middle.
What is A mean?
It's just what's left over. It's the associated anion in your acid, right? Because this is a proton when it's released. That means it leaves behind a negative charge.
So A is just a filler. It doesn't stand for an
Yes,
acid.
it's just a generic acid. Well, a generic conjugate base. This is the generic acid. That's the generic conjugate base.
Why is H2O not as strong as it? Or not as weak, or rather weaker, I guess. Why is H2O weaker than?
Well, that's a good question. There are some situations where water is a stronger base than some conjugate bases. You have to compare the K values, right? If water has a K value of 10 to the minus 14, then I would expect anything with a K value less than 10 to the minus 14 to produce a stronger conjugate base. And anything with a greater value than that, let's see. Well, it hadn't given it, but acetic acid was what? 1.7 times 10 to the minus 5? So it should be a,
1.7 times 10 to the 9.
yeah.
I'm just confused by this example, just.
Yeah, I know, because it's generic. That's the problem. We need to talk about real stuff, don't we? So let's not linger on that one for now.
Especially when we have 17 more fun-filled pages.
Yeah.
Yeah.
All right. All right, here's another generic. Let's dispense with the generics. Come on. And get on to some real stuff. All right. So here we have acetic acid, and that's the way, the modern way to write it. So you have your acetate ion right here, and there's your dissociable hydrogen. And then this one is hydrocyanic acid. And they're both weak acids. Acetic acid is stronger than hydrocyanic. All right, so let's say, I'll write it their way. Okay, and then hydrocyanic produces this and this. Okay, they're saying acetic acid is stronger than HCN. So the Ka for acetic acid versus hydrocyanic acid means that if acetic acid is stronger than hydrocyanic, that means this one is bigger than that one. All right, because it produces more of this relative to its concentration than does hydrocyanic relative to its. Okay. This one tends to put more of itself on that side than hydrocyanic puts more of itself on that side. That's what that means. Ka here is bigger than the Ka there. All right, so now that we've got that established, what does that say about the bases? Well, if this is a stronger acid than that one, then this is a stronger base than that one. Right?
Is there like a numerical way to wrap your head around that, or do you just know the next?
Yeah, there are values. Right, so this would be 10 to the minus fifth, like 1.7 times 10 to the minus fifth. I forget what this one is. It's like maybe 10 to the minus 10th or 12, something like that. A lot smaller. Several orders of magnitude.
So stronger acids produce weaker bases.
Right. So that means this is a weaker base than that one is. And since we've already established that chloride comes from a strong acid, it's the weakest base. So it's going to be the weakest over here somewhere. And then we just have to decide where does water fit in all that. Well, we showed it, and well, let's see, 10 to the minus fifth, and water is 10 to the minus 14th, right? So the water being 10 to the minus 14th, what does that say about its K? It's over here, right? Because it's 10 to the minus 14th. So that means if it's a weaker acid, it makes a stronger conjugate base. Oh, but it's given us water. All right, so what's water going to serve as a base? Well, it's a proton acceptor. So is it going to accept protons any stronger, more strongly than either one of these? It's probably going to be in here. That's where I'd put it. Okay, so let's see what the reasoning is. This is water, and there's your KW. Okay. So weakest to strongest. Okay, so I got it backwards. Weakest to strongest. So I guess right. I put water close to chloride, and these guys over here by themselves.
Is chloride the only base weaker than water?
Now there are others, like any of these. Right, will do. Actually, chloride is a weakest to strongest. Oh, yes, that's right. So to the left of chloride would be bromide, and to the left of it would be iodide.
And I guess to the left of it would not be at.
I'm not sure what astatine is, because it's radioactive. So probably not too many people work with that one.
So without having any values attached to any of these bases and acids, I'm feeling a little lost on how you actually know which one is stronger than the other than just.
Okay, so we're gonna, I guessed right. The Ka for HCN is 10 to the minus 10th, thereabouts. Right, it's, when you have the values, you're more likely to get the answers right, because that's quantitative. Up to that point, we were sort of guessing. Okay. I want to look at let's see. Okay, so we better look at this one. The value of K for the reaction. Okay, so now we're going to combine reactions. So we've got this acid combined with this conjugate base of an acid, HF, to produce that conjugate base of this acid and that conjugate acid of this base. Okay, now what we're trying to do is decide, is the value greater than 1, less than 1, or equal to 1? And these are the Kas for each one. Right? So this is the Ka for the HCN. This is the Ka for the HF. Right? But it's reversed. So what do we do with that? So what does each Ka mean? Well, for the Ka for HCN is very small. So there's a strong drive for it to remain just like that. It doesn't want to give up its proton to F minus. The HF is small, so there's a strong drive to remain over here. So that means if this is a weak acid, small K, that means this is a strong base. So there's a tug of war between these two. Weak acid, strong base. Which one wins? Come on. Oops. Wait a minute. Went too far. Let me back up. There we go. Need a break?
I do.
Give me a chance to think about how I'm going to say this. I'm sorry?
So I just need times.
Yep. Been there. That's why I carry them with me.
Oh.
1, 2.
Not too. Thank you.
I take Zantac too. Huh?
What's that?
It's a proton pump inhibitor.
Which would be useful for this kind of cat.
Yeah, it's over the counter. My wife takes generic Prilosec.
I might get that shot actually. It afflicts me all the time. This does give me a moment to ask you a question that will completely derail the discussion that we're having. But so if I were to take hydrochloric acid and put a drop in my palm, it would fall through the table. Why?
If it was concentrated.
Well, yeah, okay, but what about donating hydrogen? Makes it eat through like things, makes it.
Okay, that's only part of the reaction. Yeah, when biological systems interact with strong acids, there's more than just acidity at work.
There's more than just a hydrogen donation.
Yes. You've got that chloride that's available to react with other tissue components.
Like it'll just, I don't know what skin is made of on a chemical level, but it'll take things from the skin. It'll like the chloride will take things from the skin, and then the skin will no longer, it won't be skin anymore, it'll be something else.
Right. Plus, strong acids like that act as hydrolyzing agents. That is, they break bonds.
Interesting. Hydrolyzing.
For instance, if you have a fat, then you increase the hydrogen ion concentration to a certain point, and it causes those ester bonds to break.
Fatty foods, and your body releases more HCl in your stomach.
Yeah. Yeah, it's like pre-digestion. There are two types of hydrolysis. There's acid hydrolysis and base hydrolysis. In that case, if you use base instead of acid, strong base with fatty acid, with true fat, it's got a special name called saponification. And that produces glycerol and soap.
So if I were to take lye, put it on my stomach, it would turn to soap.
Yep. You can wash your clothes with it. Okay, so we're down to point 3. We've established 1 and 2, what the drive is for each one. Then the Ka for HCN is much, much less than the Ka for HF, right? This one is very small, 6 orders of magnitude less than the HF. So what happens? HCN wins because it hangs on to that hydrogen more strongly than this one hangs on to its hydrogen. Right? So the smaller Ka value here versus that Ka means that it's going to be like this. The drive is more to be like this than the drive to be more like that. That makes sense, or did I need to say it again some differently?
Hydrocyanic acid is
This one right here.
a stronger acid than
It's a weaker acid.
it's a weaker acid.
Weaker acid than this one, right? That's 10 to the minus 10 versus minus 4th.
It's a weaker acid, yeah, but it wants to stay that way more than.
Yes, it doesn't want to give up its proton. The
See, when I
drive.
think of it wanting to stay itself, I think it's strength. It wants to stay itself. Like, that's
It doesn't want to give up the proton.
so why?
So
But then with the
Yeah.
hydrofluoric.
HCl or HCN? Oh, hydrofluoric.
So
Yeah.
the hydrofluoric
Uh-huh.
acid is a stronger acid, but
Right. In other words, it wants to give up its protons more readily than this one does. Right?
But I thought we were just talking about how it, because of the size of the.
Well, yeah. Look, 10 to the minus fourth. If it were a strong acid like its neighbor, HCl, that would be like, I don't know, 10 to the 10th. Positive 10th. It would give up its hydrogen readily, but it doesn't. HF is a weak acid. That's why this is 10 to the minus fourth. And when you write it like this, and you see that that K value is 10 to the minus fourth, that says it wants to be over here, right?
But not as much as HCN.
Right? So that means
HCN wants.
this is very small,
So
but HCN is even smaller.
So HCN wants to keep to itself even more so.
Yes,
So hydrocyanic acid is a weaker acid than hydrochloric acid.
yes. So that means it's going to stay over here.
Well, that's citric acid. I can only imagine it would be very, very, very much weaker.
Well, citric acid, okay, you're getting complicated before our time. Citric acid has 3 protons. I might as well tell you now, since we're on the stream of consciousness. So let's see, let's abbreviate citric acid like this. Excuse me. Citric acid, but it has 3 protons, right? So what does it do? When it dissociates, it goes 1 proton at a time. That's the way it goes, because you have a K value for each proton, right? So this is going to have a Ka1 for that proton. Then this one dissociates to produce the second proton and this ion. Okay? So that's another K value. Then that one gives up its proton to produce this one. Okay? 1 proton at a time. Okay. This is where I can say, always and forever, this is the way it happens. That one is greater than this one, is greater than this one. So the drive to give up a proton is greater for this one and lesser for this one than that one. But this one is even lesser than that one. And how do you rationalize that? One good way is, once you've got a negative charge on here, it's harder to pull a positive away from it. And if you've got a 2- charge, it's even harder to pull that one away from it. Okay? So as you strip additional protons off of that multiprotic acid, it becomes more and more difficult. So these values get smaller, smaller, and smaller, weaker and weaker. Right? So the first one could possibly be a strong proton, and that is the case for sulfuric acid. Only the first proton is strong. It's just the way it is. I mean that's the empirical evidence. So you get this plus this. Right, this is strong. But when you dissociate this one further, that's weak.
Okay, so the strong acid wants to readily get rid of a proton.
Yes.
strong acid in its highly reactive?
In the sense that it reacts with water, transfers its proton to water, and makes a hydronium, yeah. That's a reaction.
Is that why it's
Let's see. I think we've covered that, haven't we? Well, sort of. We've covered that when we talked about solutions. Heats of solution. When the amount of energy required to, remember the 3 steps. When something goes into solution, some energy is required to remove that proton. Then some energy is required to make a hole for the solute. And then you get some of that energy back when you associate this proton and that anion with water molecules.
But it would take less energy, right, as the strong acid, because
Right.
it readily wants to, so it just takes less energy at that point.
Right. It takes less energy to do this, and it takes the same amount of energy to make a hole in water as any other acid. So what happens is the association of this one and that one with water molecules, when they hydrate, you get a lot of energy back, more than you put in. So it gets hot. That makes the whole process exothermic. And that's why we say, do as you ought to add acid to water. Add a little bit of acid to a lot of water, then you're less likely to exceed the boiling point of water and spatter. If you add water to acid,
Watch out.
then you get hot enough to boil that water instantly. Same with bases. Strong bases will do the same thing. Okay. So Ka for the overall reaction is less than 1. How did we come to that? Do we add the two together? I'm not sure how we come to that.
Well, I mean, they're both already less than 1.
That's true. Yeah, that's a way to think about it. Mhm.
Ka equal to CD over AD.
Yeah, it's a little more complicated than that because water is involved. Water has its own equilibrium that has to be accounted for. That's why in the next slide, I think, I want to talk about Kb. We've talked about Ka over and over and over again. But Kb is a valuable concept. Yeah. Kb in terms of the base. So let's use, for an example, acetic acid. Okay? So here's our acetic acid. I'm going to use their abbreviation. Right. I'm going to leave out the aqueous stuff because it just takes too long to write that. So what happens? We get C2H3O2 minus plus our proton. Right? And our K value for this one is that one times this one divided by that one. Okay, we've already covered that. We know about that. Now, suppose we allow this one to react with water. It could happen as a consequence of putting that acid in with water, or we could add this ion independent of the hydrogen ion. Say we have the salt, the sodium salt, the sodium acetate, and we add it to water. So we're only adding the acetate, and we're not adding any hydrogens. Okay? So let's add the acetate. However we get it in there. So it's going to react with water.
don't you have to write the sodium part?
No, because it's a spectator.
Okay.
Right. If you look at sodium hydroxide in water, it dissociates. It's a strong base, so it's over here, almost 100%. And it doesn't want to come back. Right? So if the sodium's there, well, the sodium is there, it's not going to react with anything.
Or sodium. Look down.
Okay, so it's going to pick up a hydrogen from water and leave hydroxyl. Right? So we write a KB for that one, which is this C2H3O2 and the hydroxyl, and then we have C2H3O2 minus. And water, right? Leave out the L's. Okay. Water doesn't count. So that's our KB for the acetate ion. So far, so good? Sure. Right. I haven't broken any rules yet, I don't think. All right. So we know how to add equations, don't we? Suppose both of these reactions are going on at the same time. You added some of this and you've added some of that, which is basically what we do when we make buffers. But we'll talk about that in the next chapter. So if we add these together, what do you get? Well, notice, this is on that side and this is on that side. They cancel. Okay? This is on that side and this is on that side. They cancel. So what do you have left? You have water. And then you have hydrogen ion, hydroxyls. Okay? So how do we, remember how we do the, how we get the K value for a combined reaction? Remember from the last chapter? You multiply them, right? The composite K for a combined, for an added reaction is the product of the two. So we multiply that one times this one. Notice what happens. If we multiply this one times that one, sort of in your mind, just kind of shift them out here, that one times that one. Then this is on the top, this one's on the bottom. This is on the bottom, that one's on the top. So what do we have left? That's it. And what is that equal to? KW. Remember? KW is hydrogen ions times hydroxyls. Or hydroniums. We may have written it that way. Same thing. So KW is equal to KA times KB. All right? So if we have a KA for that acid, then we can write the KB. All we need is to rearrange. Let me do that.
So is this with any acid being put in water?
Yes.
Okay, I can accept that as magical. All right.
So if we know the Ka and we want to find out what the Kb is, we solve for the Kb, and it's just Kw divided by the Ka. So anytime you have a Ka value for an acid, you want to find the Kb for its conjugate base. You just divide the Ka into the Kw, and the Kw is always 1 times 10 to the minus 14. Okay?
I think I will picture that.
I wanted to put all that stuff on a slide, but I don't have the tools to do it here. It just occurred to me that it's not part of the slide. So I'll have to do it later and then put it on Blackboard, so access it if you want. Oh, plus you'll have the Zoom.
So this is,
But this is an explanation of how to calculate Kb if you only know Ka. If you know Ka for the acid, you can find Kb for its conjugate base. That's the whole purpose of this exercise. Yeah, and in that case, you just trade places. Ka equals Kw divided by Kb. Yep. All right. Take it on faith.
there's my,
Okay. So now, can unpause. So, we want to calculate the K for this reaction, right? We, in previous slides, we determined that the K should be less than 1. But we want to find out what the exact value is for that expression. Okay, this is the acid part for hydrocyanic acid, right? And that's the acid part for hydrofluoric acid. Okay, notice that this one's backwards from what we would expect there. This is the hydrocyanic expression for Ka. This is the Ka for HF. But we can't add them together because HF is turned the wrong direction, right? Right? So we need to invert the equation. And when we invert the equation, that means we're calculating Kb. Then we're going to continue on the second slide. So when we add those equations together, I think I skipped a step. See if it'll back up. Okay. So now we'll add this equation together with that equation. And we should get that equation right there. Okay, so the hydrogens cancel and leaves us with the equation that we wanted. And then, since we combine those equations, we multiply the Ka times the Kb. We determined what the Kb was here. So when we multiply those together, we get a K for the reaction of 10 to the minus 7th, and indeed, it is less than 1.
That only useful acid reactant and an acid product.
This method should work with any combination of reactions. But since we're talking about acids and bases, yes, the answer to your question. When you have an acid reacting with a conjugate base of a different acid to produce the conjugate base of the first acid and the acid from the conjugate base of the second one. Yeah.
It'll come to me eventually.
Okay. Now, up to this point, we've been talking about K values. We're gonna, I don't know, have you been exposed to pH before, how to calculate pH?
How to calculate it? Yeah, you just strip it.
No,
yeah, I know that one.
that's not a calculation. That's a test. if you know the hydrogen ion concentration or the hydronium, either one fits in here. Then Sorensen, who was the Danish, maybe, or Swedish, I can't remember which.
The O with the line there. It's
Yeah.
not scale things.
Yeah, he was tired of using those big numbers for concentrations. He wanted something a little easier to handle. So he did a log transformation of the hydrogen ion concentration and called it pH. So if you take the log of the hydrogen ion concentration, for instance, say we have 10 to the minus 7 here, okay? What would the log of 10 to the minus 7 be?
Log of 7 times 10.
Minus 7. Because the common log is base 10. Right? And by definition, a log is what is the power of 10 that equals this value. The power of 10 to the minus 7 is 10 to the minus 7. Okay, that's the definition of a log.
Which would be a pH of -7.
I'm sorry?
Which would be a pH of -7.
Nope, not yet. He didn't want to deal with negative numbers either. So he put a negative in front of it. So the pH of this, negative there, would be a positive 7. So remember, 10 to the minus 7 is the concentration of hydrogen ions at neutrality. That means pH of 7 is neutral.
But water is a pH of -14. Or not pH of -14, 10 to the -14.
The KW, yes. But the hydrogen ion part of that is 10 to the minus 7. So that would give you pH of 7. So when you stick your test paper, yeah, when you stick your test paper in there, if it's pure water, it should come back with a color that says 7.
So if it's basic, it's just a measurement of hydrogen plus ions.
Mm-hmm.
Actually, I don't know how to word that question here.
Okay, well, let's look at the continuum. Right? If this is neutral, this is going to be 10 to the minus 7 hydrogen ion concentration, or pH of 7. Okay? If we go this direction, where we have more hydrogen ion concentration, 10 to the minus 6, what will be the pH? 6. And if we go 10 to the minus 5th, 5, 4, 3, 2, 1. Stomach acid right in here. Right, so as this one gets bigger, this one gets smaller. So a smaller pH value is more acid. And we go the other direction. So it'd be 8, 9, 10, 11. We usually stop around 12. So at this point, 10 to the minus 12 is the hydrogen ion concentration. What's the hydroxyl concentration?
It should be very high.
Well, the hydroxyl times that has to be 10 to the minus 14, right? So the hydroxyl has to be 10 to the minus 2, right? 10 to the minus 2 times 10 to the minus 12 is 10 to the minus 14, right?
So bases are still a measure of hydrogen ions.
Actually, it's both, right? If you know this, you automatically know that one, because hydrogen ion concentration times hydroxyls equals 10 to the minus 14.
Is it the same on the other side?
Yeah, over here, if you have 10 to the minus 2, For hydrogen ion, then hydroxyls will be 10 to the minus 12.
Which is very, very, very small amount.
Yep.
Why numbers, or rather, why is it total 14? Is it just because the CI goes from 0 to 14? Was that arbitrary? Is it water?
All goes back to this. They have to multiply, add up. Have to add the, well, this times that equals that. Always and forever. That's why this relationship. So,
Is KW a suggestion of the relationship between hydrogen ions and hydroxyls?
that's not a suggestion. It's a mathematical equation.
So it is the relationship between.
Oh, yeah. In every aqueous solution, this is always true. So, we don't have to stop at pH. If we know the hydroxyl ion concentration, what would that be called? POH. Right?
It's just gotta be flipped.
Well, if we say, what would be the POH of 10 to the minus 2? It would be 2. Right? This is 2. This is 12. Wait a minute. Hold on a second. I'm getting ahead of myself. Also, the log transformation that Sorensen used can be used for the entire equation. It doesn't have to be restricted to each individual one. We can take the negative log of the entire equation, right? Negative log of the whole thing. What would that do then? What's the negative log of KW?
14.
PKW, which, yes, is equal to 14. Which means pH here and POH here, but how do they relate? When you multiply two numbers, what happens to their logs? You add them together. You add the logs when you multiply the numbers. Right? That's just the rule for logs. So that means if you know the pH, then you can find the POH, just subtract it from 14. So if this is 2, subtract it from that, and this is 12.
What does the P stand for again?
I don't know. Could be Swedish. It was Sorensen's prefix. Maybe it has to do with power. I don't know.
So pH. Stands for pH.
I mean, he invented it,
What
so
are the applications of knowing the POH? Like, we just don't ever hear that. Like,
yeah.
I mean, what are those applications?
It probably has more to do with, no, not with, you wouldn't necessarily assign a POH to like a water sample. You know, most of the time it doesn't matter. But you could determine the pH, maybe the chemistry that you want to use to determine the acidity of water. Maybe for that particular sample, it's easier to do the POH to find out what's the hydroxyl ion concentration. Then you can convert it to pH, and that's how you report your data. That's off the top of my head. Or if that doesn't work, it's probably going to show up on the exam.
Real world applications.
Yeah. Okay, what do we do with significant figures? Well, as it turns out, due to the log transformation, if you know the number of decimal places in the log itself, that's equal to the number of significant figures in the original number. So let's say we have a hydrogen ion concentration of, I don't know, 1.234 times 10 to the minus 3. Then if you take the negative log of that to do the pH, because this is hydrogen ion, then how many significant figures are you permitted to keep in your pH value? The significant figures in your pH value are equal to the number of decimal places here. So 3. You get to keep 3. Right, so 1.234 and the exponent of 3, then we take the log of it and then change the sign. So I get 2.9087. 2.9087, and I get to keep 3 because 3 here. So that means we round it off to 2.91 pH. Okay? I'm sure that's just an artifact of the logarithm, how the logarithms work. That's not going to be a significant problem for us going forward, but I thought you ought to know it anyway, just in case somebody asks. And pressure friendly parties.
Would be just a spectacular trick.
Okay, we've already talked about these pH ranges.
Wait a sec.
What? Did I do that wrong?
No, I don't know that you did. I'm just not. Oh, okay. Wait. I think I pressed the natural log button instead of the log button. I just want to make sure
Right.
I'm doing this.
It's a different
correctly.
base.
10.
E, yeah, E, like 2.303. Yeah.
Okay, so
It's
when you actually type in log of that number, it comes up as a negative number, but then it's negative in the front, so it cancels it out and it makes it 2.9.
yes. Right. Okay, we're not going to spend time on these. You can look at those at your leisure. You can calculate the pH of this value. Right, that one's easy because this is 1. If that's 1, then you just take the negative of that one and you got your pH. How about this one for POH? Actually, pH for this one. It's 4 times 10 to the minus 2, right? So 0.040 molar is the same as 4 times 10 to the minus 2, and then you find the POH of that one, whatever that happens to be, and then you say 14 minus the POH is equal to pH. And that's the pH. Notice that the pH for this one is much greater than 7, right? So that means it is basic. Okay, so what do you do if you're given the pH and you need to find out what the hydrogen ion concentration is?
Just multiply it. Put it in the power, 10 to the 5.85 power.
Yeah, otherwise known as the anti-log. So if we have, what is it? 5.85. So if the pH is equal to 5.85, what does that mean? That's the negative log of the hydrogen ion concentration. Okay? So if we want to solve for this one, first of all, we got to get rid of that negative. Right? So I'm going to put this one over here and that one over there. So the log of the hydrogen ion concentration is equal to negative 5.85. Okay? And then remember the definition of logarithms. This is the power of 10. That gives you that number. So 10 to the minus 5.85 is equal to the hydrogen ion concentration. Okay? So you just, on everybody's calculator, there's a key in there for 10 to the x. At least there is on mine. So I just move that negative here, and then I use that as the x power of 10 in my calculator. And that gives you the hydrogen ion concentration, otherwise known as the anti-log.
All right, so
There we go, step by step. Well, sort of. I skipped a couple steps.
so if you have the pH the solution is 5.85, what is the hydrogen ion concentration for this solution? And we said that the hydrogen ion the pH is equal to the negative log of that. So we're solving for the
We got about
hydrogen.
Hour.
40 minutes. Hour?
It was 12:15.
It's 11:40 right now. That means we've only got 40 minutes.
So, okay, you explained how to put that into the calculator, and I was still trying to wrap my head around it.
Yeah, you move the negative sign over here first, then this becomes the power of 10. That value becomes the power of 10 in your calculator. You need 10 to the x in your calculator. You got a 10 to the x?
Yeah.
Okay. You just have to figure out how to put it in there. There you go. Negative 5.85. And then that's 1.41 times 10 to the minus 1, 2, 3, 4, 5, 6. Yeah, 10 to the minus 6. Maybe you need to set your calculator up to spit your numbers out in scientific notation. Y'all have the same, you don't have the same. Okay. All right, so here we go. Scientific engineering. This up, scientific or something. That's 10 to the minus 6. Okay. You have to decide how many numbers to keep. So you get 3 decimals. Right? So this one really, that's not, excuse me, that's, right. 3 significant figures here. We should be able to keep 3 here, shouldn't we? 1.41 times 10 to the minus 6.
So pH is equal to the negative log times hydrogen ion.
Right. My motto is, when all else fails, go back to the original definition.
And if we know the pH, we can solve for the amount of hydrogen ions
Yep.
in a solution.
Go backwards and forwards. Okay. So I've already gone over this, showed you that little trick. Once you find out one of them, you can find the other one. Right? Because the addition of these two equals 14 every time. If the solution's neutral, then of course they're equal, 7 and 7. So to find the hydroxyl ion concentration from this one, you have 2 options. But the simplest option is to find out what the pOH is first, and then use the log transformation to give you the OH. That's the way I would do it. Subtract 5.85 from 14. Then the negative of that value as the power of 10 gives you the OH. Okay. So how do we calculate the pH of a strong acid solution? Easy. If you know the concentration that you're creating of a strong acid, that automatically tells you the concentration of the hydrogen ions in solution. So if we know that this is equal to this minus 3 molar, then we also know this. Okay, we're going to use this reasoning process. All right. What are the major species in solution? Well, we know that there's no hydrogen chloride in there. Right? It's completely dissociated. That means you got this one, and you still have water. Right? So which one matters? Well, water's not going to change at all. Chlorine has no effect on the pH. The pH is all determined by that value right there.
So we don't care that Cl is a weak base in this.
No.
All right, how did I miss how you knew what the ion concentration was over there?
Oh, because of this. I'm not even going to put the other one because it only goes one direction. Strong acids, they don't have a return. Right? It goes all the way over here. So if you know the concentration of this one, you know that one for strong acids. So if we know this one is what you mixed in the solution, then all of it is converted into this. There's 1 to 1. Right? One of these produces one of those. Stoichiometry.
Well, what about the chloride? We don't care about the chloride?
Nope. It has no impact on the pH because it's a weak base.
So, but just so my head understands, like, would there be the same amount of chloride then on the other side?
Oh, yeah. Yeah, sure. Yeah. That would also be equal to that concentration.
But I guess, like, the part of me is like, how did you know? Just they know from observation that the hydrochloric acid just all the same amount on the other side.
Mm-hmm. Yeah, it matches the experimental data. That's the only explanation for what for the effect that you see.
Strong acid is very inclined to give up its protons.
Right.
For this the same amount of concentration of hydrochloric acid in the hydrogen ions in this particular case.
Mm-hmm. That's where we are. We got a long way to go, folks.
It's a lot to understand in a really short period of time.
Let me take a look at our schedule.
You do have that week off your school break.
Especially when you have a student that actually is trying to understand it. Really a lot to ask.
Yeah. The only advantage to spring break is that gives you extra time to study, but it didn't give me extra time to present.
Unless you came in on an off day and recorded yourself at that.
Pick up where we left off. I could do that. It shouldn't take me as long because there won't be any questions.
Yeah. True story. True story. Sorry.
4 little anecdotes from me.
Okay. So now you can calculate the pH because we know that everything that went into solution ends up as the acid. That's simple. There's no problem there with equilibrium. You don't have to do any equilibrium calculations to see how much is left over, how much stays as the acid, how much dissociates. We're going to do that next, of course. This is like a predecessor. Am I still recording? Oh, yeah. Okay. Okay. So that was just another. Same thing happens there. What if we have nitric acid is added to water? This reaction takes place. Right? Why is this reaction not likely? You have the nitrate. Right, let's go back. Right, you form the nitrate and the hydronium. Nitric acid is a strong acid, right? That means nitrate is a very weak base. It doesn't want protons at all. So when we say, why does this not happen? Because nitrate could care less that water has a proton. It doesn't want it. So that reaction does not happen.
That's something to do with the electronegativity of NO3. It's not really strongly attracting.
Yes. It's a fairly large ion with that one negative charge spread out way around. So the attraction to protons is very weak.
Because the
charge density.
In the electrons, I guess oxygen, we'll say that's wanting an electron. It kind of changes, right? Like at one moment in time, maybe this oxygen will be completely satisfied with 8 electrons.
Oh.
And then another one of them will be.
You're talking about resonance. Yeah. Yeah. Right. It resonates among 3 different forms.
NO3 is nitrite.
Nitrate.
So nitrate doesn't care about hydrogen ions?
Nope. Doesn't want them.
Why is that?
Because it is. That's all I got.
Because the charge density is very low. It's a big ion. Let's see, we've got that, and that, I think. Like that.
Okay, so with charge density being low, you mean it's bigger, so it's more spread out.
Yes. Right.
Like if I were to have
Which means it attracts protons or other positive charges for that matter very weakly. That's why all the nitrates are soluble, right? Because they don't attract positives, cations very well. So any cation associated with the nitrate is going to go right into solution. It just gives it up. Okay. So we got to decide which reaction controls the pH. This reaction is always taking place in aqueous solution. But the question is water the major contributor of protons or hydroniums? You know, if there's a strong acid around, no, it's not, because water is a weak acid. Here we go. I guess it's not going to give me any more there. So calculate the pH of a solution that's this molarity of HNO3. Well, fortunately, it's a strong acid, so you know what the hydrogen ion concentration is. It's just equal to HNO3.
Oh, did we really answer that question? What reaction controls the pH?
Oh,
Water the contributor?
yeah, let's back up. Right, when we're talking about nitric acid in water, the one that controls is the strong acid. Nitric acid is stronger than water as an acid, so it's the one that controls the pH.
Wouldn't that make H2O a base in this?
Yeah. Right, that's the acid, that's the base. There's the conjugate acid, and there's the conjugate base.
What if you mix?
I'm so confused.
And then money situation.
Okay, so that was a prelude to solving weak acid equilibrium problems. So now that's not Le Prelude by Franz Liszt either. Yeah. Which is a fabulous composition. Just sit down and listen to it. It's amazing.
I hate to say it, but my only knowledge of Franz Liszt is because he gets kind of parodied in books when
Yeah. Yeah, he was a Polish composer living in Paris. Mm-hmm. So first thing you do is list the major species in your solution, because you've got to decide which one is actually contributing to the final pH outcome. Then you decide which species can produce hydrogen, or which species can consume hydrogen for that matter. They left that part out. Then you gather the equilibrium constants for the reactions that you've written. Sometimes you have to calculate them from known equilibrium constants. Then you decide, all right, once we've decided which one is dominant by comparing those values, like we did before. Yes, then you can write the equilibrium expression for the one that controls the equilibrium. Then you set up your ice table. Once you've got the controlling reaction written out and balanced, then you can set up the ice table. You can fill in the known values, the unknowns, or whatever they may be, and then solve for your unknown values. And then to check yourself, you have to substitute those values in the equation and see if you're within 5%, just like we did with equilibriums. Now, if it's a very weak acid, more than likely, there's going to be some portion of that expression where you can just drop that X term out. But you still need to prove that it's 5% or less. And then if the question asks for pH, you just do that calculation. Okay, so here's our example. Hydrocyanic acid at 0.8 molar. Right? What are the major species? All right, we're just considering this reaction in the beginning. There's no question involved. What are the major species? Right? Well, since it's a weak acid, right, it's going to be mostly HCN. That's it. And water. Right? Water is always a major species. But major species won't be hydrogen ions, and it won't be cyanide ions either. Oh. There. I just said why these are not major species. Because it's a weak acid.
It wants to stay.
Wants to say it's CN.
Doesn't want to give up the hydrogen.
Right. So, we write our expression. There's our major species reacting with the other major species to produce these two, and there's the constant for that reaction. Then we have, that's what happens with this one. What happens with this one by itself? Well, water reacts with water is this one, right? So which reaction controls the pH? The one with the larger K value.
So you see it.
Right, so this one controls right here. Right, that's the one that we want to work with for our equilibrium expression, or our ice table. But they're not going to let us do it. We're going to pick up a different one.
So, you already switched.
Oh, sorry.
I guess I have to apologize
There we go.
for having a slow brain, but I'm just like, so this is the, this is breaking it down into the 2 steps, taking that acid, putting it in water, it splits into hydronium and cyanide.
Mm-hmm.
And then what are we saying? We add more water?
Oh, we're taking water, we're taking the major species and saying, what do they do in this environment?
Oh, okay. So
Okay.
separately, this is what this acid does with water. And
That's
this
what
is
it does.
Water does with water.
Yes.
And so,
Then we compare the K values for each of these reactions. The larger K value is the dominant one, right? Because what does that mean? That means it's more likely to produce these than this one is. By, in fact, 4 orders of magnitude. So it definitely controls the reaction.
so that Ka value, that constant was determined, and
That's given to you.
we just know it was already.
Yeah, it's either given or you find it in a table.
That's why it's KA.
So Ka is a given, just like the Kw is a given.
Right. Oh, you might as well memorize that one.
Okay. But you go with the larger K value to decide what is controlling the pH.
Yes,
KW always tends to be -14,
always.
no matter what acid or bases are in play, it's always tends to be -14.
Right. At 25 degrees. If you change the temperature, you change the equilibrium. Remember that? So we're gonna keep things at 25 degrees just for simplicity's sake. And in fact, you can change the temperature up or down 10 degrees and it won't significantly affect the equilibrium. So how about this one? 0.5 molar HF with a Ka of 10 to the minus 4, right? So what are the major species? Well, like before, HF and water, right? Instead of HCN, it's HF this time. Right, we compare the reactions. So that's what HF does with water. This is what water does with water. So this is the controlling reaction.
So H and F are not major species because HF is a weak acid.
Yes, true. Okay, so we set up our ice table where HF reacts with water to produce hydronium and fluoride. We say the initial concentration is 0.5, and these concentrations are not exactly 0, but they're insignificant compared to this one, right? Because the starting concentration would be what? For water, would be 10 to the minus 7th, right? But this one would be 0. So 10 to the minus 7th is so small compared to that one, we can ignore it. All right, that's why I put the approximate here. Actually, that one shouldn't be approximate. That should be actually equal to 0. Because pure water doesn't have any fluoride in it. We've taken that fluoride out. So what's going to happen? Well, some of this is going to disappear. And the ratio here is 1 to 1. Equal amount shows up here, equal amount shows up there. So the equilibrium expression is going to be this. But the equilibrium values will be that, that, and that. So we say, what's our Ka equal to? Right? Our Ka is this one times that one, right, from here, divided by this one, there, equals that value. So we plug in our numbers, right? So we have X for this one, X for that one, and 0.5 minus X for this one. And we're going to say that since the dissociation is since it's such a weak acid, the production of this relative to that is going to be so small, we can say, well, that term is really going to be 0.5. But we're going to leave this one alone because we still have some of that we have to account for. So we're going to set it equal to that and solve for X. So there's our concentration of X, which is the concentration of hydronium. So, right. So we can calculate the pH from that, 1.72. Let's see, are we going to, oops, sorry. There's that manually.
Why can you use the concentration of hydronium?
In this expression?
Yeah, why can you use that?
Go from here to here, is that the question?
No, my question is, you calculated for X and you said X for hydronium and you use that same value to calculate the pH. I guess I don't understand how you go from that to that.
Yeah, why not use 0.50 minus X as the final value for pH?
No, 0.5 minus X is actually what's left over here. That doesn't tell you the pH. pH is based on X.
So the side of the reaction still has a little bit of hydrofluoric acid. Without it being the H given, it's just neutral. Like the HF is neutral, but doesn't actually influence the pH of the solution until it turns into hydroxyl.
Yeah, hydronium, yeah.
I guess that's what I don't understand. Why does the hydronium equal the spot of hydrogen ions?
Because we chose it that way.
No, that's not what I'm asking. Why is, because I thought the pH was calculated by the amount of hydrogen ions.
Well, yeah.
But why does hydronium equate to hydrogen ions?
I feel we would just turn to H plus and bottom.
Yeah, well, H plus is a convenience. It doesn't exist. Hydronium is how the hydrogen ion exists. But we use H plus for convenience. Right? Otherwise, we'd have to say, instead of pH, we'd say pH3O plus.
Okay. So is there any other expression of hydrogen that would work in that situation? Because I'm just like only looking for H plus, but I didn't know that H3O would be what I would be looking at.
Yeah.
So is there another expression of hydrogen that works in that, the pH equation there?
No.
It's only just hydronium?
Yeah, it's either H plus or hydronium. Yeah.
Okay. That's where you lost me. I didn't
Okay.
know.
Okay, let's see. Oh, this is where we're checking ourselves. We're taking the equilibrium expression and plugging that value back in to be sure that we're within 5%. So if we plug that in here, then our Ka value that we calculate is this, and the Ka value that we are given was this. So we compare the two and find that, yes, we're within 3.9%. So that assumption of X being much, much smaller than 0.5 is true. Percent dissociation. This refers to how much of your acid actually dissociates. It's similar to the concept of equilibrium constant versus equilibrium position. Right? The percent dissociation depends upon the concentration of acid. but the constant does not. The constant, the Ka, will be the same no matter what your concentration is. But the percent dissociation will change. And it's just the amount of dissociated acid in molarity divided by the initial concentration that you put into the solution times 100. All right, here's the weird phenomenon that you observe with weak acids. The actual percent of the acid that is dissociated increases when the concentration goes down. In other words, you decrease the amount of acid that you put in solution, but the percentage of it that dissociates increases. Okay? So I got to prove that to you, don't I?
I'll take your word for it.
Wait a minute. I thought I was going to prove that in the next slide. All right. Oh, we're going to use it. Okay, this is actually using that value. So if we have a solution of 8 molar formic acid, right, the stuff that fire ants use when they bite you, formic acid. That's why they sting so bad. Well, that's one of the reasons. It's a nice little cocktail that they inject into the wound. Formic acid is only part of it. There's some other things in there that aggravate your skin and make that little pimple pop up. It destroys tissue is what it does. Okay, so if we're given that for this solution at that concentration, it is 0.47% ionized in water. Right? And from that, we can calculate what the Ka is. Right? We start off with this one, right? Because we're going from that value to this one, which would be hydronium, would work just as well, and this one. So we start off with 0 there. But 0.0047, which is the decimal equivalent of that value, is what the change, the negative change for this one, because it's being used up. And since it's a 1-to-1, then we're actually, it appears over here as that, and here is that. Then we can calculate the values, right, because we have real numbers and no x's. So that's a real number there, real number there, real number there. Now we just put those into the Ka expression, and we can calculate what the K is. Come on, there we go.
So why is it minus 8? Like, how do you know that?
Because it's the change.
All of it? So we're saying all of it is going into?
No, just this amount right here.
All right, where does the 8 come from?
Oh, okay. So
That's the original amount that we put in a solution.
all right. So we're
Yeah, 8 molar.
Okay. So 4.47% of 8
Mm-hmm. That's what disappears.
is the change.
Mm-hmm.
Okay.
So once we've got these values, we can plug them into our expression and find out that the K is 1.78 times 10 to the minus 4. Once you've got the K, then you can do other calculations, right?
Just back to realization. I always wondered why, you add HCl water, you get hydrochloric acid on this. The H ion is what would, makes it acidic. Why doesn't it just go away because it's gas? It's because it's not an H ion, it's actually it's the H3 or H3O, which is
Okay.
Is that why?
Yes, because it's bound to the water.
It's not actually just an H ion. That
Right.
would just go away.
Right. It's associated with the water molecule. And in order to have to make this become this, this has 2 electrons. This has none. So you have to supply the electrons to get that bond to form before you can make gas.
So if you had 2 H pluses, it would.
They'd stay in solution. You got to add electrons. which is what we do when we electrolytically split water molecules. Right? The direct current supplies electrons, and the electrons are what reduces the hydrogen ions into hydrogen gas.
So electricity is just electrons.
Has to be direct current. Okay, so we can calculate the pH from the value that we determined as our hydrogen ion concentration. So the value, this is a trick question. The value of Ka for a 4 molar formic acid solution should be what? Higher than, lower than, or the same as?
4 molar formic acids as opposed to 8 molar.
What effect does it have on Ka? Zero. Ka doesn't change. Ka is a constant, right? So it doesn't matter what the concentration is, the Ka is a constant.
Unless you change the temperature.
Yeah, okay. With that one caveat.
Honestly, that's just because of the last, well, what we just did, the last test, that kept tripping me up.
Oh, okay.
Because you add more of something, it's like, how does this affect K? It doesn't. It doesn't affect K, this K is constant. The only thing that affects K is the temperature, with, Kc and Kb.
Yeah.
Kept tripping me up, so.
Okay. You don't get your shots in, right?
Yeah.
Okay, the percent ionization of a 4 molar formic acid solution should be higher than the percent ionization of 8 molar, based on what we said 2 or 3 slides ago. Whenever you decrease the concentration, you increase the percent ionization.
Ionization being defined as the amount of the acid that's turned into H2 or H3O.
Yes, as a ratio. Okay,
It increases the percent that ionizes.
yes.
But maybe not the total quantity that's ionized, like the actual number. Maybe just a larger percentage of 4, but like 75% of 4 is less than 60% of 8.
Exactly, right. It's a percentage. It's not an absolute value.
And is that because with the larger amount of, with 8, there's some of it going backwards, right?
That's a good way to look at it, yeah. The reverse reaction,
Equilibrium.
Yeah. So let's, we're going to have to use a generic acid for this one, sorry. So if we have an initial concentration of our weak acid as HA, and that's our equilibrium expression. And there's the Ka that associates with it, right? We've done that before, right? So what happens to how do we calculate the actual value of HA? Well, we have the initial, that little 0 means initial concentration of HA, minus part of it that changes was roughly equal to HA actual, because there's so little of it that changes, right? So we can say that the hydrogen ion concentration and the A minus are equal to X. So we can put X in here and X in here. And we can just put HA down here like we did before, right? In the denominator, we said, yeah, the difference is so great, we can throw that X out. So that's what we're going to do for this generic. So there's our expression for the initial conditions, right? That's an unknown, and we're going to take this as the initial value, right? All right, now that's our expression at for Ka for the initial conditions. What happens if water is added? Right, we're going to decrease the concentration of our HA.
The percentage that dissociates goes up.
Yeah, but we're going to prove it. Right, so what happens if water is added such that HA becomes 1/10 as strong as before. Okay, here's what it looks like. These new values then are X divided by 10. They were X to begin with. Now they're X divided by 10 because we've diluted them. But this is before equilibrium, right? We've Le Chatelier'd them. We've disturbed them by adding water. And this is initially what they did, all right? So when we plug the values in, the new values in that we've diluted here, which way will the reaction go? Well, we're going to calculate Q now because we don't have an equilibrium situation. So we calculate Q. So Q then is 1/10 of each one of these, right? So it's actually 1/10 of Ka is Q. So if our Q value is less than Ka by 1/10, which way is the reaction going to go? It's going to go toward products. If Q is less than K, the reaction moves toward products or to the right. That means a higher percentage dissociation. Okay? I'm going to go back and review Qs. Q compared to K, what happens? Okay, we're out of time. So let me mark this place, and I will try to finish the. Let's see, let me find out where I'm
Brain
at.
cell activity is slowing down anyways. That's the point of the day.
Okay, where am I? Dissociation. Oh, here we are. Okay. 142. That one. That. Okay. What's the date? 4th. So we've got up to here on the 4th.
Right, so
So I need to finish that one and get to the next one, and then post it.
-5.
Do you think realistically, that'll be something